Hi, I'm Niv, and I'm a research scientist at PlyOps. Our paper is called The End of Moore's Law and the Rise of the Data Processor, and this is joint work with a list of people on the slide, as well as the entire wonderful PlyOps team. Moore's Law is gradually coming to an end. This means we can no longer rely on CPU advances to eliminate computational bottlenecks. At the same time, SSDs have become widely used, and they exhibit the interesting property that writes are more expensive than reads, and that random writes are especially expensive. Overall, these trends pose challenges for storage engine designers. The first challenge is in choosing a core data structure. For example, in order to optimize for SSD writes in CPU, many storage engines today simply log data in storage and index it using a hash table in memory. The trade-off is that the hash table used to index takes up a lot of memory, and so it becomes expensive in a different way. The deeper problem here is that any data structure that optimizes for some cost metrics tends to also penalize others. Similarly, compression is becoming more painful to manage. On one hand, it reduces storage writes in space, but on the other, it can easily become a CPU bottleneck. And the last challenge is with resilience. In order to recover from power failure, a write-ahead log and double write buffering are typically used, but these techniques amplify the cost of writes. Moreover, recovering a failed drive using RAID is becoming more expensive as it requires rewriting an entire replacement drive. And furthermore, even if a small part of a RAID stripe is updated, the error correction code also has to be rewritten, and this involves an expensive read-modify-write operation. Fortunately for us, hardware accelerators, such as FPGAs, ASIC, and GPUs, are becoming mainstream. Such devices allow to offload particularly compute-intensive tasks from the CPU. And so our first insight is that such accelerators can also be used to address non-compute bottlenecks. The intuition is that they enable algorithms and systems that expand computation more lavishly in order to optimize for other cost metrics, such as storage I/O or memory. Yet we observe that even with more devices like accelerators plugged into a server, orchestration and administration overheads for the system increase. There may also not be enough slots in the server to connect all the devices we need. And so our second insight is that by encapsulating as much functionality as possible within one device, we can better scale data movement, administrative overheads, and the number of tasks offloaded from the CPU. Based on these insights, we introduced the PlyOps Extreme Data Processor, or XDP. XDP consists of an accelerator, an FPGA or ASIC, some memory modules, SRAM, DRAM, and flash, and some capacitors for power safety. It provides storage engine functionality, compression, encryption, fail safety, and it exposes either a block device interface or a key value store interface to the application running on top. So here's how it works. XDP is connected to the host through a PCIe interface. It can connect to the underlying SSDs through the host, or it can connect to them directly for better performance. Interestingly, storage is completely decoupled from the XDP device, and so it is possible to use whichever SSDs are available. The application at the host inserts key value pairs to XDP. In case the block device interface is being used, the key is in LBA and the value is a 4 kilobyte block. Data is then immediately placed at a capacitor-backed SRAM buffer within the device. This allows for extremely fast commits without the need for a write-ahead log or double write buffering. Data is then compressed using ZSTD, a compute-heavy algorithm which is normally a CPU bottleneck. The accelerator, however, makes ZSTD viable and allows us to write less to the SSD and store more on it. We then place the entry within a 2 GB buffer in DRAM. When this buffer is full, we store it via RAID 5 on the underlying SSDs. And since we only issue large sequential writes, we never update a part of a stripe, and so we avoid the expensive read-modify-write operations of RAID 5. The storage devices eventually fill up with block clusters, and meanwhile, we maintain a hash table index in DRAM to map entries in storage. This index can also be stored in the host, but even if so, we do all the processing of buckets using the accelerator to offload work from the CPU. Now, updates and deletes issued by the application are performed out of place, and so they lead to the invalidation of data. To reclaim space, the system picks the block clusters with the least amount of valid data left and garbage collects them. Overall, this design provides very low write amplification, far lower than that of other common data structures like B-tree or LSM tree. Now, during recovery of a failed SSD, our RAID 5 subsystem exploits its full knowledge of the data in storage via the index to only copy valid data to the replacement SSD. This significantly reduces recovery time. And now, a very important question is how to design the hash table index. Some log structure designs store the full key of every entry and map it to the precise block containing the entry in storage, but this can take up a lot of space. Other designs store a fingerprint instead of a key for each entry, where a fingerprint is a hash digest obtained by hashing a key. While fingerprints take up far less space, they lead to false positives and thus redundant storage IOs. In order to restrict tail latency for our clients, it was important to eliminate false positives. And at the same time, to be cost effective, we also wanted to dramatically reduce the memory requirement relative to other designs. So to address both goals at the same time, we designed a novel data structure called the delta hash table. And it's different from existing designs in two central ways. First, before we write each block cluster to storage, we sort it using the accelerator. We then exploit the fact that data in storage is partially sorted to reduce pointer sizes. And secondly, we only encode the delta or difference between fingerprints that coincide within the same bucket, rather than storing the full fingerprints. So let's now see this in more detail. Suppose we have two entries with keys K1 and K2 falling in the same bucket, along with pointers P1 and P2 to the locations of the entries in storage. We first generate a fingerprint for each key, and we make sure this fingerprint is at least 12 bytes long to make sure the probability of the collision is negligible. We then identify the most significant bit that differentiates between the two fingerprints. Here it happens to be the second bit at index 1. We then create a trie with one internal node containing the index of that first different bit to distinguish between the two entries. Suppose another key K3 then gets inserted into the bucket. Its first three fingerprint bits are the same as for the second entry, yet the fourth bit is different. And so we encode that bit index as another internal node that distinguishes between entries 2 and 3. In the leaf nodes, we store the pointers to the locations of the entries in storage. This delta trie ensures that the fingerprints are fully differentiated. Therefore, no false positives can take place. This in turn guarantees that queries to existing entries cost strictly 1 IO, and as a result, XTP provides great tail latency. In order to also achieve low memory footprint, we encode this trie succinctly using some metadata about its topology. In the paper, we show that this requires at most 3 bits per entry. Furthermore, each pointer takes up only around 2 bytes, and this is because data is partially sorted in storage, and so we do not have to store full block addresses. In order to achieve good hash table utilization, we store multiple of these delta trie buckets contiguously within larger superbuckets. The superbuckets absorb the size variability of the tries, such that only a little space is wasted on average at the end of each of the superbuckets. The trade-off is that we now must parse an entire superbucket to access a given trie and the entries within it. But fortunately, we have the customized hardware at our disposal to accelerate that process and prevent it from becoming a CPU bottleneck. Overall, the hash table takes less than 3 bytes per entry, which is at least a 3x improvement relative to log structure designs in the literature, and a 10x improvement relative to designs in industry. And remarkably, XTP achieves this while preventing false positives completely. Effectively, we're able to exploit the accelerator to design a computationally expensive hash table that in exchange requires little memory and exhibits no false positives. This demonstrates that accelerators can indeed help us solve non-compute problems. We ran an experiment with TPCC on MariaDB, a SQL OLTP database, which is in turn running on the XTP block device. XTP is running here on top of 4 SSDs using RAID 5. The baseline is the same, except without XTP and using RAID 0, which does simple striping and does not provide fail-safety. Note that we're being unfair to XTP in this experiment, as RAID 5 spends some of its storage bandwidth on storing error correction codes. At the start of the experiment, we observed that the baseline exhibits poor performance relative to XTP. The reason is that MariaDB is based on a B tree, which issues random writes to the SSD. In contrast, XTP converts all of its IOs into compressed sequential ones, and it also eliminates double write buffering. And so, remarkably, the XTP system wins despite also having failure protection. We then replace one of the drives in XTP to simulate it failing. We observe that even as the XTP system recovers, it still outperforms the baseline. Recovery finishes after only 2 hours, and at that point performance returns to normal. All in all, we introduced the PlyOps Extreme Data Processor, which we view as the one device needed to make any workload hardware conscious and friendly. Thanks very much.